Let's do problem 14. So here we've got an equation, and it looks like what they want you to do is take that function and rewrite it so that you apply transformations that will make the graph look in various ways that they want it to be. So I guess there's two steps here. One is deciding what transformations need to get applied, and then you have to remember how algebraically do you actually do that. So I'm going to do this problem 6, and then I'll leave problem 7 for you. So it looks like, so the horizontal distance here is 0 to 3, so that's 3, and it looks like 2 to 5 is also a horizontal distance of 3. So I don't think I need to horizontally scale it at all. It does look like I need to vertically scale it, because the height here is 1.5, and the height here is 3, so it seems like I need to double the height. Okay, so vertical scaling. It also looks like I need to translate it horizontally by 2. So let's take a minute and sort of remember how do you apply transformations algebraically. So here's a different but related function. This is root 1 minus x squared. So let's just do a bunch, and then we'll go back and think about why. So in order to apply a horizontal transformation, I'm going to be substituting something for x. So for example, if I substitute x minus 3 in the place where x used to be, that's translated at right by 3. That might seem backwards, because negative 3 might seem like I should be going left, and we'll talk about why that is in a minute. But if I substitute x plus 3, where x used to be, now that's translated left by 3. Scaling is like multiplying, so if I substitute 2x, where x used to be, that it's the same height, but now it's horizontally scaled it by kind of squishing it to be half as large as it used to be. And again, notice that feels backwards, because I multiplied by 2, so why is it halving its width? If I multiply it by 1/2, that now has stretched it so that it's twice as wide. So again, sort of backwards. All right. That was all horizontal stuff because we were modifying x. What if we modify y? So it's the same thing. If I substitute something for y, so I'm going to replace y with y minus 3. Oh, where is it? There it is. So, seems backwards, right? Minus 3, and yet it is translated up by 3. And again, we'll talk about y in a minute. Notice, though, that replacing y with y minus 3 is the same thing as if we'd added 3 on the other side. And there it kind of makes a little more sense, because if these were the old y values, now I'm just adding 3 to whatever the old y value was. So it's like you take all the old y values at their same x positions, and you just move them up by 3. And so that kind of makes more sense. Again, scaling is like multiplying, so if I do 2 times my old y values, it's like I've taken every single height at its old x value and just doubled it. I've just multiplied it by 2. Okay, so let's go back and talk for a minute about why, when you make a substitution for x, is the effect backwards from what you think it should be. Here's kind of a good way to think about it. So I'm going to replace x with 2x, and it's had this effect of kind of squishing it by a factor of 2. Well, okay, what point is this? This is at an x value of 1, and if you think about plugging in 1 right here, that makes this entire expression 0, which is why it's an intercept. Well, okay, what about this intercept? What you want to think about is remember, x used to be my input. Now, 2x is kind of like my input. So I'm thinking, what x value do I need to plug in so that 2x is going to be the same as my old x value? Because remember, my old x value of 1 is what gave me a y value of 0. So I'm thinking, if this whole thing, if 2x were equal to 1, I should get the same y output, right? And if you think about it, so if I make x equal to 1/2, now when I multiply it by 2, that gives me a value of 1, which gives me my y value of 0. In other words, when x is equal to 1/2, it gives you the y value that you used to have when x was 1. And the reason why is because whatever x value you have, you're doubling it before it becomes input to your old function. So the reason it's all backwards is because you sort of have to think about the x values. You have to undo whatever's happening to them here in order to figure out what they would be so that they're the same as the input to your original. I don't know how much sense that made, but you can think about it, again, if you replace x with x minus 3. So like when x is 1 up here, that produces y value of 0. what would x have to be here in order to produce the old value of 1? Well, it seems like if I plug in 4 for x, now that's given me a value of 1 on the inside. And sure enough, the value at x equals 4 is the same as the value of x equals 1 in the old function. All right, so hopefully that all makes some semblance of sense. Let's go back to problem 14. So there's the given function. Remember, we wanted to do two things. We wanted to translate it right by 2, and we wanted to scale it vertically by a factor of 2. So let's do the scaling first. So if I want to scale it vertically, I'm changing the y values, and I just want to double them. So I'm going to multiply them by 2. So there we go. Now it looks like this vertex is at a y value of 3. Perfect. All right, now I want to translate it. Remember, translating, I'm going to substitute in for x, and that needs to be true wherever x appears. So I'm going to replace x with x minus 2 in both places that it appears. And there we go. I've shifted the whole thing right by 2. So why don't you give number 7 a try using those same ideas, and maybe if you want to, you can make up a couple more just to get it really in there. Good luck!